Nobody warned you about this. You were told the Cassini mission ended. You were told the spacecraft burned up, dissolved into Saturn's clouds, and that was it. The story was over. But what if the story was never over? What if the data Cassini sent back before dying was so enormous, so layered, so terrifyingly dense with secrets, that scientists are still pulling revelations out of it years, even decades, later? What if the final images weren't the end of Cassini's mission? What if they were the beginning of the most important question humanity has ever been forced to ask? There is a moment, rare in the history of science, when a machine built by human hands looks back at us and shows us something we were not ready to see. September 13th, 2017. A spacecraft the size of a school bus, traveling at over 77,000 miles per hour, pointed its cameras one last time at the Saturn system it had spent 13 years studying. It photographed Enceladus. It photographed Titan. It swept its lenses across the rings, across the storms, across the darkness between worlds, and then it dove into the atmosphere of Saturn and ceased to exist. What it left behind was not silence. Although the spacecraft may be gone, its enormous collection of data about Saturn, the giant planet itself, its magnetosphere, rings, and moons, continues to yield new discoveries for decades. Let that sit for a second. Not years. Decades. We are living inside those decades right now. And what is emerging from that data is not what anyone expected. To understand why what is happening right now in 2025 matters so deeply, you need to go back to the beginning. Not the beginning of Cassini's death, but the beginning of what Cassini actually was. This was not a simple telescope pointed at a distant planet. Cassini was launched in 1997, carrying 12 scientific instruments and a separate probe called Huygens, and it traveled for 7 years through the void of space before arriving at Saturn in 2004. That alone is worth pausing on. 7 years of travel, a machine built to survive the radiation, the cold, the silence of deep space, and then to orbit one of the most complex and beautiful objects in the solar system for 13 years without stopping. Every orbit was a data-gathering mission. Every flyby of every moon was a chapter in a story that humanity was writing in real time without fully understanding what it was writing. But here's where it gets interesting. Most people remember Cassini for its images, those breathtaking photographs of Saturn's rings backlit by the sun, of Titan's amber, haze of Enceladus erupting like a broken snow globe. What most people are not seeing is that the images were the least important thing Cassini sent back. The real payload was invisible. It was data, atmospheric composition, magnetic field readings, gravity. On measurements so precise, they could tell you the internal structure of a planet from the outside. The grand finale produced the first direct measurements of the narrow region below Saturn's rings and led to a startling discovery. We had never been inside that gap. No spacecraft in human history had ever passed through the 1 to 100 mile space between Saturn and its innermost ring. And when Cassini did it, 22 times in its final months, it did not find what the models predicted. Think about what that means. For decades, scientists had built mathematical models of what existed in that gap. Calculations going back to the 1970s had made specific predictions about the density, the composition, the behavior of particles in that zone. And Cassini walked into that space and found something different. Initial results indicate that hydrocarbons appear to be descending into the atmosphere from the rings, that electric currents flow between the inner rings and Saturn, and that a new radiation belt exists in the gap and innermost ring. A new radiation belt. Previously unknown. Found in the last months of a spacecraft's life as it prepared to die. That is the moment you realize that even our MO-St. confident scientific models of this solar system are working with incomplete information. And this is where everything changes, because that finding, the electric currents, the hydrocarbon rain, the hidden radiation belt, was just the opening line of the story Cassini's death dive was telling. Published across 6 major papers in the journal Science and 5 additional studies in geophysical research letters simultaneously, the grand finale results created something close to a scientific earthquake. Saturn's magnetic field has poles that align nearly perfectly with its rotational axis. And that is deeply strange. Every other magnetic planet we know of has a tilt between its magnetic axis and its rotational axis. Earth has one. Jupiter has one. Saturn should have one. But it does not. Or at least, if it does, it is so small that Cassini's instruments could barely detect it. That is not supposed to be possible according to the dynamo theory, the leading scientific model that explains how planets generate magnetic fields. Something deep inside Saturn is doing something we cannot explain. And we only know this because Cassini flew close enough to measure it directly. Let that sink in for a moment. We have been studying Saturn for 4 centuries with telescopes. We sent Pioneer 11 past it in 1979. We sent Voyager 1 and Voyager 2. And yet, it took a spacecraft diving between the planet and its rings to reveal that we fundamentally did not understand one of the most basic properties of this world. If we were this wrong about Saturn's magnetic field, what else are we wrong about? The answer to that question is still being written, and the most recent chapters are the ones that are shaking scientists the hardest. Because the magnetic field mystery is not even the most alarming thing Cassini revealed, not by a long distance. What Cassini found on the rings, and what the rings are doing to Saturn right now, is the kind of discovery that forces an entire field of planetary science to sit down and reconsider its assumptions. Unlike the rings, which are 95% water, hydrocarbons comprise most of the material falling from the rings into Saturn's atmosphere. Water ice, pure frozen water, is what the rings are made of. But what is raining down into the planet from those rings is organic chemistry, carbon-based molecules, complex hydrocarbon compounds of the kind that, on Earth, are associated with the chemistry of life. Saturn is being rained on from above by organic material, every second of every day. It was a phenomenal surprise to discover the high mass of material flowing into Saturn's atmosphere and how complex its chemistry is. But here's where it gets worse. That organic rain is not just interesting chemistry, it is evidence of something deeply inconvenient. Because if organic molecules are raining from the rings into Saturn, they are not staying in the rings. They are being lost. And the rate at which they are being lost has enormous implications. At the current rate, the inner rings would last only tens of thousands of years, much less than the age of the rings, which are at least 30 million years old. Tens of thousands of years. That is nothing. In geological time, in astronomical time, that is the blink of an eye. What this means is that we are living in a rare, privileged window of cosmic history during which Saturn happens to have its spectacular rings. They will not always be there. Future intelligent life in this solar system, or future visitors from elsewhere, will look at Saturn and see something different. And we are among the only observers who will ever see what Saturn looks like right now. That realization alone would be enough to make Cassini's data permanently significant. But the universe, apparently, had more to say. Because while scientists were processing the ring discoveries, while they were untangling the magnetic field anomaly, while they were cataloging the hydrocarbon rain, another portion of Cassini's data was sitting in the archives, waiting. And in December 2025, a new paper published in the Planetary Science Journal revealed something that had been hidden in the grand finale data for 8 years. During its final orbits in 2017, Cassini discovered a hidden halo of dust particles reaching up to 3 times the planet's radius. The rings do not end where we thought they ended. There is a halo, an invisible extension of Saturn's ring system stretching out to 3 times the radius of the planet itself. We could not see it from Earth. We could not detect it with the instruments of previous missions. It took Cassini's cosmic dust analyzer, flying through the material directly, to find it. And it sat in the data for nearly a decade before anyone knew it was there. Read that again. 8 years. The discovery was sitting in the data, unnoticed, for 8 years, not because scientists were careless or inattentive, but because the data Cassini sent back is so vast, so deep, so multi-layered that there simply are not enough human lifetimes to process all of it at once. And what else is sitting in there? What other revelations are waiting for the right researcher, the right analytical tool, the right moment? According to informed sources within the planetary science community, we are still only beginning to understand what Cassini actually found. The implications of this are enormous. And then there is Enceladus. This is where the story stops being about physics and starts being about something far more profound. Something that, depending on what the next decade of science reveals, may be the most significant discovery in the history of civilization. Enceladus is a moon of Saturn. It is small, only about 500 kilometers across. You could fit it inside the state of Texas. And for most of human history, it was considered nothing more than a minor, icy satellite, unremarkable except for its unusually bright surface. Then Cassini arrived, and in 2005, it found something that nobody was prepared for. Shortly after arriving in orbit around Saturn, the Cassini mission found plumes of water spraying up from Enceladus' south pole, clinching evidence that the moon harbored a liquid water ocean underneath its bright white icy crust. A liquid ocean. Underneath ice, on a moon so far from the sun that it receives only a fraction of the solar energy that reaches Earth. The immediate question, the one that every scientist in the room must have felt simultaneously, was obvious. If there is a liquid ocean, and if there is heat driving it, and if there is chemistry happening inside it, then the question of whether life exists on Enceladus is not a philosophical exercise. It is an active scientific investigation. Cassini flew through those plumes. It flew through them directly, collecting material from an ocean that had never been touched by any instrument built by human hands. And what it found in those plumes has been the subject of continuous, escalating study ever since. Because with every new analysis of Cassini's data, the case for Enceladus being a habitable world gets stronger. Analysis of fresh plume material from Enceladus confirms the presence of organic molecules, key, K-CHNOPS elements, and abundant hydrogen, supporting the existence of a global subsurface ocean with hydrothermal activity. These findings indicate that Enceladus possesses essential ingredients and energy sources potentially suitable for life. K-CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These are the 6 elements that biochemistry on Earth is built on, and Cassini found 5 of them in the plumes of Enceladus, 5 out of 6. Think about what that means. You are looking at a moon 886 million miles from Earth, and you are finding the chemical alphabet of life. Not life itself, not yet, but the letters that life uses to write itself into existence. The results revealed a range of aromatics, aldehydes, esters, ethers, and alkenes, as well as hints of nitrogen-oxygen compounds. With earlier Cassini discoveries of salts, hydrogen, and phosphates, this means 5 of the 6 KNOPS elements essential for life have now been detected. Sulfur is the only one left to find. Only sulfur is missing, and what makes that detail extraordinary is not what is missing. It is the implication of what has been found. These are not simple molecules, aromatics, aldehydes, esters. These are complex organic compounds. On Earth, they are precursors to biological chemistry. They are the kind of molecules that, given the right conditions and enough time, can organize themselves into something that moves, reproduces, and responds to its environment. But here's the layer beneath that layer. The question is not just what molecules exist in Enceladus's ocean. The question is where they are being made, and whether the conditions producing them could also sustain biology. And that is where the most recent science, published in late 2025 and early 2026, becomes genuinely extraordinary. Saturn's gravity pulls and squeezes Enceladus as it orbits the planet, creating cycles of heating and cryogenic freezing. Evidence from Cassini suggests this is enough to create hydrothermal activity on Enceladus's seafloor, like hydrothermal vents on the seafloor on Earth. Hydrothermal vents. On Earth, deep ocean hydrothermal vents are among the most productive ecosystems on the planet. They exist in total darkness, without sunlight, without photosynthesis, producing energy from chemistry alone. And they harbor extraordinary life: microbes, tube worms, shrimp, fish, entire food chains built on chemical energy rather than solar energy. Cassini's data suggests that Enceladus may have the same thing. Not probably, not speculatively. The data points there directly. And this is where everything changes. Because in November 2025, researchers published a paper in Science Advances that may be the most important Cassini-derived finding yet. Researchers uncovered evidence that the ocean on Saturn's moon Enceladus is in balance. Now, the ocean loses as much heat as it gains, boosting its prospects for habitability. This is not a small technical detail. This is the difference between a temporary ocean and a permanent one. A temporary ocean might last a few million years before the heat source dies and the ice reclaims everything. A balanced, stable ocean can persist for geological time, billions of years. And life, as we understand it, needs time. It needs the same conditions, sustained across enormous timescales. Enceladus's ocean may have that. The data suggests the North Pole also emits heat at a greater rate than can be explained by purely passive models, indicating that the heat balance at Enceladus is active, not remnant. Both poles are producing heat, not just the south, where the famous geysers erupt. The north as well, quietly, persistently, as if the entire moon is alive with thermal energy, maintaining an ocean that should not, by any simple calculation, still exist. What most people are not seeing is that this changes the entire calculus of the search for extraterrestrial life in our solar system. For most of the 20th century, the search for life elsewhere was focused on Mars. Mars had water in the past. Mars had a thicker atmosphere. Mars had conditions that might once have been Earth-like. And so the robotic missions went to Mars, and the funding went to Mars, and the public imagination went to Mars. But Cassini's data from Enceladus is forcing a quiet but powerful pivot. In revealing that Enceladus has essentially all the ingredients needed for life, the mission energized a pivot to the exploration of ocean worlds that has been sweeping planetary science over the past couple of decades. The lessons from Cassini are now being directly applied to NASA's Europa Clipper mission, currently studying Jupiter's moon Europa, another world with a subsurface ocean, another world where Cassini's discoveries changed what we thought was possible. The real story is that Cassini did not just study Saturn. Cassini rewrote the map of where life might exist in the universe. Before Cassini, we thought life required sunlight. We thought the habitable zone around a star, that narrow band where liquid water could exist on a surface, was the only address where biology was possible. Cassini proved that heat can come from inside a world, from gravity, from tidal forces, from the friction of a moon being pulled and squeezed by a giant planet. And if that is true in our own solar system, then it is almost certainly true throughout the galaxy, throughout the universe. Suddenly, the number of potentially habitable worlds does not shrink to a handful of Mars-like planets orbiting Sun-like stars. It expands by orders of magnitude to include every ice-covered ocean moon orbiting every gas giant in every solar system that has ever existed. The implications of that are so large that the human mind almost refuses to hold them. And yet, what is perhaps most disorienting about all of this is the nature of the evidence itself. Cassini is gone. It burned up in Saturn's atmosphere on September 15, 2017, and we have no way to go back and collect new samples. The data we have is the data we have. Every new discovery, the hidden dust halo, the stable heat balance at Enceladus's north pole, the complex organics in the plumes, the new radiation belt, is extracted from a finite, fixed archive of information that a spacecraft gathered before it died. Scientists are not making new observations. They are reading an old message more carefully. Our study highlights the need for long-term missions to ocean worlds that may harbor life, and the fact that the data might not reveal all its secrets until decades after it has been obtained. Decades. The mission ended in 2017. We are 8 years in, and the discoveries are accelerating, not slowing down. What does that tell you about what is still in there? What does it tell you about the depth and complexity of what one spacecraft, built in the 1980s and 1990s, managed to capture in 13 years of observation? The instruments Cassini carried were cutting edge in the mid-1990s, but the tools we now use to analyze the data, machine learning algorithms, improved mass spectrometry techniques, more refined atmospheric models, are vastly more powerful than anything available when the data was first collected. We are rereading Cassini's notes with eyes we did not have when the notes were written, and the text keeps revealing new meaning. Consider the specific mechanics of what happened in October 2025, when a team of researchers led by Nozer Khawaja at the Free University of Berlin published a landmark study in one of the most prestigious scientific journals in the world. They had been reanalyzing a Cassini sample, specifically material collected during a direct flyby of Enceladus's plumes, where the spacecraft flew through the geyser material at close range rather than collecting it from the distant E-ring. The difference matters enormously. The high-speed flyby of Enceladus enabled researchers to identify new compounds that were not found in the E-ring data, most notably esters, alkenes, and ether compounds. The E-ring data had been analyzed for years, but the direct plume flyby data, collected at much closer range, contained signatures that had not been fully extracted. Esters, alkenes, ethers. These are not exotic, obscure molecules. They are compounds that appear in Earth's own biological chemistry. They are compounds that, on this planet, are produced by living systems and by the chemical processes that support living systems. According to informed sources within astrobiology circles, this particular finding was treated with unusual seriousness precisely because of how specific and robust the identification was. This was not a vague spectral hint. This was direct chemical identification of compounds that have no obvious non-biological pathway to explain their presence in the quantities observed. That does not mean life was detected. Let that be absolutely clear. But it means the chemical environment of Enceladus's ocean is producing the kind of complex organic chemistry that, on Earth, we associate with biology. Whether that is a coincidence, a precursor, or an actual sign of living systems cannot be determined without going back. And we have not gone back. This is where the story becomes as much political and economic as it is scientific. Because going back to Enceladus is not simple. It requires a mission. It requires hardware. It requires funding, political will, international cooperation, and somewhere between 10 and 15 years of planning, construction, and travel. The data from Cassini is screaming that Enceladus needs to be visited, not with a flyby, not with a spacecraft that simply dips a sensor into a plume, but with a dedicated mission that can land, drill, sample, and analyze in ways that Cassini could not. The scientific community knows this. I'd look for life in the plume of Enceladus, send a probe into Saturn's atmosphere, and maybe land something to explore the lakes and seas on Titan carrying the next generation of instruments. Those are the words of mission scientists who spent decades with Cassini and now understand, with a clarity no one outside that field can fully appreciate, what the next step must be. But the next step is not funded. It is not approved. It is not scheduled. The most important scientific question humanity may ever face, are we alone in the universe, has a promising address, and we do not yet have the will to knock on the door. And beyond Enceladus, there is Titan, Saturn's largest moon, a world so complex, so layered, so strange that Cassini spent 13 years studying it and still left more questions than answers. Titan has a thick atmosphere, denser than Earth's. It has lakes and seas on its surface. It has weather. It has a hydrological cycle, not water, but liquid methane, raining from methane clouds into methane rivers and pooling in methane seas. It is, in many ways, the most Earth-like body in the solar system, except that it operates on chemistry that would kill any life as we know it. Or would it? Because there is a growing body of theoretical work suggesting that life in liquid methane is not impossible. It would be radically different from life in liquid water. It would use different chemistry, different energy pathways, different molecular structures. But the physical and chemical logic does not rule it out. And Titan, sitting there in Cassini's data, is a world waiting to be understood.